My name's Vincent. I'm from PyData Amsterdam, and today I will talk to you. So the name of the talk is SaaaS, Sampling as a Algorithm Service. And what I will talk to you about today are basically the joy of sampling algorithms, how they work, why they work, and when you should actually use them. So in short, I'm going to first explain sampling methods as a concept. It's always important that we understand the concept. And once we've understood the concept, I'm going to show you how to build the concept in a simple Python for loop. I'm then going to sort of get into the depth and explain that this concept is also useful for machine learning. We're going to apply the concept to a Kaggle problem. We're going to apply the concept to a time series task. And then I'm going to compare the performance of this sampling approach to something we build up in TensorFlow. So very simple. I mean, most of us have probably seen this example before. The best sort of idea of explaining sampling is usually by doing this task. Assuming you've gone to a college where sort of you're doing programming for the first time, you've probably done this exercise where you're trying to estimate pi, and you do that by drawing a circle, and the circle is between a 1 by 1 square. You draw random points within this 1 by 1 square, and at some point you have enough points that you can estimate pi, because the relationship between the area of the square and the area of the circle is such that you can derive pi from it. I'm assuming people have seen this exercise before, and I'm assuming that this is something you know of sampling. This is a way of getting sampling right. And if you do this often enough, then you get a nice measurement of pi. What's cool, though, is this is sort of what I would call direct sampling. Like you have a space, and you're directly sampling from it. But alternatively, what you could also do, just as a concept, is you can say, you know, instead of sort of sampling directly, how about I just pick a random point somewhere, and sort of like a frog, I hop around. And if I do this forever and I keep hopping around in the search space, I might also just estimate pi well. Sort of as a conceptual idea. You can also do the frog hopping and sort of get a Markov chain going. Then your thought at the moment might be, hey, that seems logical, but something might go wrong here. Namely, you know, the frog is going to eventually jump outside of the square. So we need to do something about that. So there's these boundaries, and we only want to explore regions that we are interested in, and we cannot have our poor pebble go to infinity. We may need to twiddle a bit and sort of think about the Markov stepping rule if we really want to estimate pi well. We have a direct sampling approach, but we need to find a way to get this indirect sampling approach to work. So there's two ways of doing this, I guess. I mean, one way would be if the pebble jumps out on the left side, we make it reappear on the right side. There's one thing we could do. But there's a bit of math involved if you want to prove it. An alternative might also just be, instead of going out to the left, how about we stay where we are? And then sample a point which might be in the region we like. Okay, so I hope at least we have two ways of sampling, and if we do this, then we'll also get to pi. So we have a direct way of sampling, and we have an indirect way of sampling. This is the first concept we need to have in our head before we move on to higher levels of abstraction. But we can use direct sampling or indirect sampling to get an estimate of pi out. This indirect sampling won't be as random initially. We kind of have this, we need to have this chain be very long before we actually get something that's sort of nice and random enough. But if we do this for, let's say, millions of times, then at some point this will be random enough so we can get an unbiased estimate of what pi is. So we've just seen sort of a Markov chain being used to infer value of interest. So let's see if we can maybe do this for other values. Because this is an example with pi. Maybe let's start doing some more data science-y stuff instead. I hope the main concept is clear, though. We can use a Markov chain to get variables we want from interest. Instead of doing that with pi, let's now assume that I have some data points, and I'm assuming that this data comes from a normal distribution. And I would really like to discover what normal distribution the data might have come from. And for those of you who might need a bit of mathematical remembrance, remember that a normal distribution has two parameters, a mu, which says where is the center of my normal distribution, and a sigma, which says how sort of skewed is it to the tails, or how peaky is it? High sigma means there's lots of variance. Low sigma means there's low variance. So instead of getting samples for sort of a region where I'm trying to estimate pi from, what I'm going to do now is I'm going to sample values for mu and sigma. Before I had sort of an x and a y coordinate that I was going to sample. Now I'm going to sample around in the mu and sigma space. Because the idea is, if I sample around, I also might get an idea of what a good estimate for mu is and a good estimate for sigma. And when I'm doing this, I also wouldn't mind being able to quantify the mu and the sigma and the randomness I would have. So same idea. Let's just pick a random value of mu somewhere and a random value of sigma. And let's do a Markov chain in the parameter space. And let's do this lots and lots and lots and lots of times. And we get this chain with lots of these values. And again, you could wonder what might go wrong here. And it's the exact same thing as with the pi example. Because if you think about it, if we're sampling such a thing, this is the Markov chain you might get. Let's say we start over here, and at some point, we end up in a space where sigma is negative. Well, obviously, sigma is never going to be negative. There will never be a normal distribution where there's no variance whatsoever. So if you just sample randomly, just like before, you might leave a region of interest, and we need to think of a way that we can prevent this. So what might be a nice way for us to stay clear of areas we don't like? Because we don't mind sampling in areas that are likely, but we don't want to sample as many times as in areas that are not likely. So we need a kind of way to score the sample that we get. So how about I'm standing here and I'm considering going there. I'm the pebble, I'm about to jump. If the score that I have now is less than a score that I will have, then probably the next sample is rather likely, and I should always do the jump. If where I'm right now, and this next step seems to be going in a less likely direction, we should maybe consider standing still and exploring a different area. So I'm now using a concept of a score, and what is a good score? Well, so in this example, right, we have a couple of data points, and we're going to figure out what a nice mu or a nice sigma might be. And I'm assuming it comes from a normal distribution. How about I take all the data points that I have, I map that to the normal distribution that I'm currently considering, and I just multiply all these likelihood values. If this is a good estimation, then most of the likelihood should be in an area that is sort of likely. So it's actually not a bad measurement, maybe. And again, I'm standing right here, there's a mu and a sigma. I'm moving to a next area where there's a different mu and a different sigma, and I need a way to say this point is better or worse than that point. So this is a score you could get. This is a normal distribution. This is sort of the likelihood that we have, that we get this data, given that we have a certain mu and a certain sigma. And here we have a slightly different mu and a slightly different sigma. And you'll notice that the likelihood score that we get out is slightly different. The y-axis will change in the next picture, but let's say I now have a likelihood that is very broad. The likelihood might actually get worse as well. Okay, let's take this likelihood approach. I haven't yet done any full math proofs. It's also not my goal of this talk. But we have a nice way to say, hey, the current place of the pebble is better or worse than the next place of the pebble, and we can sort of compare. So we're still sampling, that's the idea, but we still need to discuss the scores a bit, and this seems like a nice path to go on to. So we can calculate the score now. We at least discovered what the score should be. Let's now maybe make it more tangible with an example. So let's say I have some parameters A, that's where I'm now, and I have some parameters B, which is where I might be going. We need to find a way to say, hey, when do I jump to B and when do I stay in A? How about we just compare the two scores? So we do a coin flip. If it's twice as likely that I should stay as opposed to going, I do a coin flip. If it's below 0.5 or something like that, I stay, otherwise I go. Now, I've told kind of like a very quick fairy tale of how I might do this. So let's do a bit of recap, because I just discussed quite a bit. We have some data, and we have some parameters we want to estimate. And we're going to use sampling. We're going to do nothing fancy. We're just going to do sampling. We're going to sample around the mu and sigma space. So those are the two numbers I need to define a random distribution that is normal. The way we're going to sample is we're going to say, hey, starting from some mu and some sigma, if the next mu and sigma is more likely, do a move. If not, compare the two likelihoods that I have, flip a coin, and then decide to stay or decide to go. And then we're just going to repeat this a whole lot of times. The hope is that at the end, I will have lots of mu samples and lots of sigma samples, and the mu value that's more likely will also appear more often. That way, I might be able to infer what the true mu should be. And the easiest way to demonstrate that this actually works is to just build a for loop in Python. So let's code this up. First, I just import NumPy, and I import stats. I make some random numbers just so I have my starting data that I start out with. I make an array with one element that is going to hold all the mu values that I sample. And I have another array with one element that's going to hold all the sigma values that I have. I'm also going to define a step size. The step size is nothing more than something to say, hey, this pebble that I have, how big will the jump speed that the pebble is going to make? And here is a function that's kind of nice, which comes out of SciPy, that just calculates the likelihood. The only thing I do is I take the data, given a mu and a sigma, I map that to the normal distribution, and that just gives me my likelihood number that I can use to compare the score. With this in place, I just build a small for loop. Basically, every single time I say, hey, I have a new mu, which is the old mu plus some sort of random step. I have the old likelihood, I have the new likelihood, and then I'm just going to say, hey, is this new number more or less likely? If so, if it's more likely, always make the jump. If it's less likely, do a coin flip. And if we fail the coin flip, then just append the old number. We can do this, and then we have a nice array of mu, we have a nice array of sigma. And I can show you what sort of the results look like. In the beginning, we were sampling mu in an area that's not really likely, and then boom, at some point, we keep on staying in an area that is actually kind of likely. And this is what happens over time. So this is many, many different iterations, many, many different random numbers. And this is one way of looking at it, namely over time, but we can also take a sum of this and then turn it into a histogram. Again, in the beginning, we were exploring this area, but more and more later on, we're exploring this area. And this is actually kind of nice, because I can almost immediately see, like, hey, maybe the maximum likely, very likely value for the average is around here. And I also get a nice impression of how uncertain I might be that this is the actual sort of true value for mu. And as I'm doing this for mu, I'm also doing this for sigma. And again, I'm starting out in some region that's probably not very likely, and it tries to be in regions where it's more likely, and then it, at some point seems to be sampling in the same area over and over again, and I get the same sort of distribution for sigma. Another way of looking at this is not to say, hey, let's just look at sigma and let's just look at mu. What we can also do is you can say, let's look at how mu and sigma change over time. And I started mu and sigma sort of in a region that's not very likely. And you see it explore different regions. And then at some point, it determines that, hey, maybe I should keep around here. Typically, you're not very much interested in what happens in the beginning when you're doing such a sampling approach. So to make things simple, how about we just cut away the first 1,000 samples we have and focus on what we did later? And then we end up with something like this. We have still some uncertainty of what the true value of mu might be and what the true value of sigma might be, but we seem to have quantified that uncertainty in a way. So with this very simple for loop, we've actually demonstrated a couple of cool things. We've just demonstrated the idea behind sampling algorithms. The idea is you just think of a mathematical system that describes your uncertainty, so if you make a model probabilistically, and then you just sample such that you're in areas that are likely more often than in areas that you're not. And with that very simple idea, you can actually build lots of models, and you just use sampling to come to your model. A couple of benefits is that our implementation right now, sorry, a couple of facts, let's say, it's not a benefit. Our implementation is not very fast. I mean, I just wrote a small for loop. It's appending to a list. We might be doing something better if we actually know the types. So probably it's best if we use a specialized package instead of doing this with for loops. If I'm a data scientist, I might want to do something more mature than write for loops in my notebook. So probably we should use a package. And we may not need to talk more about practical examples, because in this case, of course, you could just take the mean by taking a sum and divide it by numbers in the array. So this is the first thing I did as I was trying to learn what sampling algorithms do. And just as a point in between, whenever you're trying to learn something new, this is what I learned from analyzing how I was learning this, whenever you do not understand an algorithm, build it yourself and make it as simple as possible. Quite often when you're learning a new algorithm, all it takes is a for loop or two. Try to write code that you love reusing as well. Simple helper functions like the likelihood function that I made, they make sure that you don't make unnecessary mistakes. And especially if the algorithm's new, debugging is kind of hard. What I do when I do this sort of thing, I have a separate cell in my notebook that does nothing else but have a few assert statements, just to make sure that the functions I build in between aren't the thing that makes the error. It's very annoying if you don't know if the numerical aspect is the problem or the code that you've just written. This is just a mere point in between. I now want to jump back to the fact that we actually may have gotten a nice algorithm to do data science in. So let's discuss the maths a little bit, because why is this so important and why do people care? Well, The way that Bayesians look at the world is they have this formula that you've probably seen on blogs somewhere, is we have some parameters and we have some data, and we kind of want to do inference on what might be likely values of the parameters of the model given the data that we see. And Bayes' rule basically says that that is proportional to the probability that you see this data given the parameters times the prior of your parameters. And in our example, I'm using theta here as sort of a collectible term for all the parameters that I have. In the example we just saw, that's a mu and a sigma. And the funny thing about this big D, we can also make that a little bit clear. We can just say the collection of all the data points, the way you handle that typically is you say, well, you can calculate the probability that given these parameters, this one data point appeared. And you can kind of multiply all the likelihoods together to come to one single likelihood number. And that's the cool trick that you use to say, hey, this one point in the parameter space before I jumped is more likely than the other one. And you can do log likelihood tricks here. You don't have to multiply. You can also take the sum of a log. But this is also a nice vantage point. And the main cool thing about sampling is that suddenly we are very flexible. I can come up with any sort of probability likelihood that I want. I can translate this into a linear regression or a neural network or whatever I want. As long as I can sample this, I can sample around this space and I have a likelihood, I can do inference on all of my parameters. So this is still a little bit of abstract. So let's just do two examples that show that this might be useful. And because this is a data science conference, we have to have one Kaggle example. So my favorite Kaggle competitions are the ones around Christmas, because then something always goes wrong at Santa's headquarters. In this particular example, Santa has 1,000 bags to fill with 9 types of gifts. And due to regulations at the North Pole workshop, no bag can contain more than 50 pounds of gifts. The idea is you don't know exactly how much this one gift weighs, and you have to assign a gift to a bag. If there's too many gifts in the bag will break. However, I do get information back. I do know at some point that this one bag weighed this much, which means I can kind of do inference on what the gift actually weighed. Because I might know, for example, that we had a gift that was of type horse, and if a horse gift came from this one distribution, or a train gift came from this distribution. So I know some things about these gifts, but I sort of was wondering, if I know the sum of a couple of bags, can I do inference to figure out what the actual weight of one of these gifts was? And to put that in a little bit more of a math equation, suppose that there are 4 gifts. I know the weight, I know the prior, so I have a bit of an impression of what the minimum and maximum weight of one of these gifts might be. But I mainly get the sum of the bag back. So in this situation, I could say, hey, I've got W1, which is the weight of one gift. I've got W2, which is the weight of another gift. And I only get these things back. So I have a couple of things that I know, and there's a couple of things that I don't know. So preferably, I like to be able to do inference on this, and preferably, I don't want to do this with a for loop. So how do you do that? Quite simply, just chug it into PyMC3. It's a library that just does this. It's very easy. You basically say, hey, these are the parameters that I want to do inference on, and these are the data points that I've actually seen in real life. So in this case, I can say, hey, I've got this normal variable. I'm assuming that mu is normal. And the only thing I know is that mu1 plus mu2 is, well, this is the observed value that I see. But I don't know exactly what mu1 or mu2 is. The only thing I know is that when I add them together, I get this one number out that I knew before. So let's have a pebble and sample, 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 and see what we get back. PyMC3 can make a plot that sort of looks like this. And it's the same thing as we saw before. We can, I'm doing multiple samplers here. But you can see here the iterations that I'm making. I'm making lots of them. And you can see here what we get over time. We do this for the few parameters that we have. So for the first gift, the second gift, the third gift, and the fourth gift. And it shouldn't be too much of a surprise that it's pretty sure what the weight of the third and the fourth gift is. You can see that it's very nicely converged. This is kind of logical because there's 4 unknowns and sort of 3 equations. So it's kind of likely that we really know the value of 2 of these things, but there's 1 degree of freedom. And that's what you see back here. These chains, they are sort of parallel. So there's like a green thing here that's low and a green thing there that's high. And every line you see here is from an independent chain, so to say. But we can... You don't see the mouse. Oh, I thought you guys saw the mouse. This is super embarrassing. OK, well, I thought you saw the mouse the whole time. Thanks, though. So you see a bit of green here. You see a bit of green there, right? And you see that there's a bit of blue here, and you see the exact same blue shape here, but it's mirrored, which basically means that the sampler doesn't really know what the value of mu1 or mu2 needs to be, but it does know that if this value is low, this one should be high. And that's sort of the intelligence we expect. And I was sort of wondering for this one Kaggle competition, if I submit a few things to Kaggle, can I infer what the true weights of these GIFs were? So that was sort of the main goal I had. I'll show you in a bit that this won't work, but this is a nice explanation of how inference works. There's a couple of things that I know, and given any system that I have, I just have to explain the math. I can sample, 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 and just let the sampler sort of figure out what the actual probabilities were. There are some limits to this, though. So let's say we do tons of gifts and a few bags. So in the previous situation, I had 4 gifts and 3 bags. And in this situation, I have 10 gifts and 6 bags. I can push this into the sampler, and then it sort of gives me feedback that says, hey, this is all over the place. This is a feature, though, because the sampler at this point does tell me, hey, I am totally not sure what the weight of this variable is. I can give you a maximum likelihood number, but what I'm also giving you is sort of a nice distribution that describes my uncertainty. And I don't know about you, but I like knowing about my uncertainty. This is typically what makes Bayesians Bayesians. We care about this sort of thing. So this is still a bit of a hypothetical example, I think, right? So this is a nice Kaggle thing, but what might be a sort of a situation where it's obvious that we're doing something that's useful? So let's consider the switch point problem. It's a problem. I'm not saying it's the obvious problem for this sort of research, but it's a nice problem because people can typically understand it. Let's say you have a computer system. You have lots of servers everywhere, and a change happened at some point in time. You want to know when the change happened. And you can do this manually by plotting that and then saying, hey, the change probably happened there. But probably you want to automate this because you have thousands and thousands of servers, and humans are kind of expensive to pay to check all this. In this situation, we need to define a mathematical, sort of a probabilistic system. And it's just like before. I'm interested in inferring what my parameters were given some data set that I have. Except in the previous case, I had a mu and a sigma, or a weight of a bag. And in this case, I have a switch point, a mu before the switch point, a mu after the switch point, a sigma before the switch point, and a sigma after the switch point. This is the maths, but I can also explain it with a picture, which people typically prefer. So given a tau, which denotes where was a switch point, I could say, hey, this part belongs to the first system, this part belongs to the second system. And I'm assuming that all data comes from a normal distribution with mu1 or sigma 1 on this side, and mu2 and sigma 2 on this side. And hopefully, we're going to figure out that tau is more likely to be around here than around there. And I can write it out all in the math, and this is the math of the picture you just saw before, but this is the essence of it. The main thing that we have to be very mindful of is, and don't let the math confuse you too much, the main thing that we need is we need to describe the likelihood of all the data that we've seen given the parameters, and we can split that up into, say, a prior of some sorts, and let's say a likelihood of some sorts. So this is where we're going to put the model mainly. And the model is actually kind of simple. We just say if the data point y is before the switch point, then it comes from one normal distribution. Otherwise, it comes from the other distribution. The only thing that I'm going to add is I'm going to add some sort of prior to this as well, because I know a couple of things about the system beforehand. For main point is that the switch point is an integer that cannot be shorter than 0, smaller than 0, or larger than the length of the time series. And I also know the variance, the sigma variable, should always be positive. If I ever start sampling in regions that don't adhere to that rule, I'm doing something bad. Again, this is the same recipe as I told about before. We have some data and some unknown parameters. We're going to sample around the parameter space, Markov style. If the next parameter sample is more likely, we move. If it's not, we flip a coin and decide to stay or move on. And we're going to repeat this a whole lot of times. And also here, I'm not going to go through the effort of doing a for loop. I'm going to use PyMC3 instead. So I just say we have a basic model. Oh, pardon. And I do something where I say, hey, there's a mu and a mu2 and a sigma 1 and a sigma 2 and a switch point. These are the things that I don't know. And on the line below, I will say, hey, but I need to involve the switch point somehow. So I'm going to calculate what the mu is over time by saying, hey, if the time is larger than the switch point, use mu2, and otherwise use mu1. And do the same thing for the sigma. And the nice thing is I can take that mu, I can take that sigma, I can say that came from a normal distribution. I have some observed variables. Boom, go ahead and sample. This is the plot that I get back. And again, in the beginning, it's sampling in a region that's not super likely, but eventually it gets to a point where it says, hey, most likely, this is sort of the posterior distribution of the parameter space, from which I can easily see, hey, there's a value for sigma 1, there's a value over sigma 2, and it seems to be very certain that the switch point happened there. Suppose that there was no switch point. 5 minutes, oh boy. Suppose that there was no switch point, then this would have been a very uniform distribution. However, there's only one single peak here, which means that we're pretty sure that the switch point happened there. We should be careful, though, because if we now want to say something about what was the maximum likely value for mu1, for example, the downside would be if we do a gradient search, we might get stuck in this hill. So we care about this sampling because a gradient search in this space might get us stuck. But there's two bonuses. There's less chance for us of getting stuck, and we get a nice view of how uncertain we are about this parameter. Those are the main benefits of taking this Bayesian approach, let's say. And I only have 5 minutes, so I'm definitely going to go a bit faster now. Sorry? 7, wow, luxury. By extension, what we can also do is we can consider a situation where we have 2 switch points. And the main thing that I'll just quickly jot over is that the system is kind of the same. In this case, I'm assuming that we had a situation before. We vert to a different state, and then we revert. So I'm building a model as if this is happening. And the code is relatively the same, except I have 2 switch points now. And the view, once you've sampled all of this, it gets a little bit different. The main thing that you see is that it takes a bit longer now because there's more switch points and there's more parameters in general. It takes a bit longer before we're in the likely area. So what you would typically do is you would say, OK, if this is probably unlikely area and we seem to have converged here, if we're going to talk about a posterior distribution, maybe we should only look at the variables and not include the first bit, but just look at the last bit. And things look a bit nicer. So I hope that by now I gave you sort of an intuitive glimpse of why sampling algorithms are nice, and that PyMC3 might be a nice library to play with. I will end on a sort of more critical conclusion, though, because I now showed you guys all the benefits of sampling. But let's be critical and wonder, can we also do this in a different way? Because you can wonder, do we need sampling? If this is the mathematical system that we have, I mean, I can also just see this as some sort of function where these are parameters that I have to sort of optimize. I can also maybe just say, hey, just do gradient descent in that space. I mean, we could do the sampling and you get the posterior and all that's very nice, but if you're just interested in the maximum likely value, you could maybe just do this in a sort of parameter search, right? How about that? So the code's too long to discuss, but this is the code that you need to do this in TensorFlow. And I basically implemented what I just said in TensorFlow, just to see, hey, is this statement true? Can we get similar results just by doing a gradient search? Why TensorFlow? There's great support for gradient methods, and the logging is for free, because you get TensorBoard, which is nice. So I ran this, and what you see here is just the likelihood that I ended up with. What you see here is the value for tau that I found, and the mu1, the mu2, the sigma 1, the sigma 2 values. You see that there's a bit of noise. The reason that there's noise is because I'm doing this on simulated data, and every run gets a different seed. Turns out, I keep on hitting the maximum likely value. In this case, I didn't get stuck in a hill. So gradient descent worked, and it solved the problem. It may not always work, though. I mean, depending on the system you define, there might be a system with lots and lots of hills, and there's a bigger risk of actually getting stuck. I do think it's worthwhile to mention this, though, because in the end, there are reasons to go for the sampling approach, and there are reasons why you might want to go for the gradient approach. Situation, for example, where you don't have a lot of data, then you usually have uncertainty, and then you typically want to have a posterior. You want to be able to describe how uncertain you are over certain numbers simply because, that's my girlfriend, simply because, it's actually kind of ridiculous. So you guys don't know the stress that I'm feeling, but my girlfriend just said over the chat that now that I'm not home, she gets to buy whatever she wants, and she's off buying a kitten now. So when I get back, it's like, Thanks, PyData, for extending my family. Anyway, if you don't have lots of data, so PyMC3 then has a nice use case, because you want to be there's uncertainty, you want to do something with your posterior distribution. Also, if you need to make like one single big decision, so you're going to do sort of a large simulation and you want to make one decision where there's lots of risk involved, then too it makes sense, because you want to be very explicit about your uncertainty. But probabilistic programming in general, namely defining a nice mathematical system and seeing if you can optimize that and be clever about it, you could use PyMC3, but other tools exist, and you might be able to use a gradient as well. The goal of this talk is to give you guys more of an intuition of how these sampling methods work, and to also give you an impression that these tools are actually kind of nice to play with. I think I have 2 minutes maybe for questions. Thanks. And also, like, thanks for listening. This was 85 slides, so you guys have been a great crowd. Thanks for sticking around.
You have like 8 minutes.
What? The 2-minute slide was for the, oh, all right. We get 8 minutes for questions, everyone.
Do anyone has a question?
Yep.
So in the first example where you were talking about finding the mean and sigma of a normal distribution given the data,
Yep.
it looked like you were kind of doing a sort of stochastic gradient descent approach in there anyway, because you're saying if I'm going to improve my outcome, I'm going to make a decision or not whether to jump that way.
So yeah, but there's one important distinction. There's still a probability that it go to a lower sort of region that's not as likely.
Mm-hmm.
A gradient algorithm typically doesn't do that. The reason being, in this case, I'm interested in finding the distribution of uncertainty over my parameter space. Gradient search is typically more interested in finding the most likely value. These two tasks are different. The Bayesian would say the maximum likely value of my posterior is not so much a special citizen. I'm interested in the full distribution. This is what makes Bayesians and machine learning specialists different, typically.
Okay, thank you.
The one thing that is actually kind of nice to show as well as a sort of extension of this, because I still have tensor. Yeah, so I was running this this morning. For those of you not familiar with TensorBoard, wait a minute. There we go. So, oh, now it's on a different screen. Where is it? There we go. So this is the same system as before, but what I've done is I have used different methods of gradient descent, sort of to check how different methods of gradient descent handle such a probabilistic system. And one nice thing that you should obviously see is depending on what gradient method you use, you can get stuck quite early. This is typical because, again, I'm doing a gradient search. I'm not exploring the likelihood of the parameter space. I'm merely looking for the most optimal one. And there's risk involved as well.
If you have to run some elements of the gradient search, though, isn't that what you're trying to replicate with this exploring the probability space? That's why it's a stochastic descent.
So yeah, but 2 steps back. Again, if you're doing a gradient search, again, you're interested in a very likely value, one such value. In this case, I'm interested in the distribution. Stochastic gradient descent also means that there's a stochasticity in calculating the gradient, not so much in finding the correct posterior. You, of course, hope that a good stochastic gradient descent and a good sampler reach to a similar conclusion that doesn't that supports one another. This, however, doesn't have to be the case, especially if you've got thousands of parameters.
Hi, great talk. Thank
Thanks.
you. If you go to the plot where you show the switch problem,
The
time series.
first one or the second one, and I have to press this.
Any of them.
So I press this button, then you see, yeah. No, not this one. I believe you mean this one.
Yeah, well, like with the switch point. Yeah, that one.
Yeah.
So I can see that this is something useful to kind of detect regimes, right, in time series data potentially.
Sure, yeah.
So what happens, like, from what I can see here, is that your mu and your sigma are kind of constant or have a mean value, right?
So obviously that's an assumption in my model, right?
Yeah.
There are more mature ways of dealing with that.
Yeah, because I was going to ask, can these be applied as well when you don't have necessarily like a constant mu and sigma, but you have a drift in your time series, a constant drift?
Yeah, so there's some ways of dealing with it, but that's sort of the art of being the Bayesian. I will first show the math and then come back to this, because the whole models is here. How I relate this switch point to any model, I could also say the front bit and the back bit, they're both different linear regressions. And then I have a switch point, and there's a constant and a slope on that end, and there's a constant and a different slope on this end. I have to do, I have to be kind of careful that I do the math well, but you can do whatever system you want here. The sampler will just figure out, given this system, what are likely parameters and how certain are we of them.
Okay,
So
thanks. And just
the modeling step is here, for example. Here I'm saying it's from a normal distribution and that's it. But I can also say, well, this comes from W's a normal distribution where it's W0 plus W1 times whatever time step, and there's also some uncertainty there. And you have to do more modeling, let's say, but you still have the full flexibility. If people are interested in this, come up. If enough people want it, we can do it on conference, and I'll show you some more demos of this. But typically, you have full freedom in that sense. What you could even do is you can say, hey, here's one instance with this system, here's a different system, here's a different system, and then find the most optimal parameters for that one system, and then compare the likelihoods of all these systems. Because the system itself also gets a likelihood parameter.
Thank you.
Good thing we have like 8 minutes for questions. Nice.
I think in PyMC3 there is a sort of the most popular, the default sampler, which is the no U-turn.
So first of all, yes, there's multiple ways of sampling, of course. The way the pebble jumps, you can do that in different ways. For example, if this is a two-dimensional space, I can jump directly to a new place, but I can also first jump in the x direction and then in the y direction. But there's also many different ways that you could sample, and PyMC3 just has support for lots of ways of doing that.
Right.
Yeah, so I don't know if this answers your question because I interrupted you, but okay. But I was applying inference in my mind to figure out what you were. Yeah.
Hi, that's a really great talk.
Thanks.
How similar would the distribution be for the parameter values if you just used bootstrapping instead of this approach?
So it does feel similar, right? So typically what you could do for bootstrapping, for example, which is a nice exercise as well, is you can say, take a subset of the regression that I'm doing, find the most likely value for the slope and the intercept, take a different subset, repeat, 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 repeat. So one would immediately assume, yeah, there has to be some form of similarity. It's just that the sampling methods are slightly different, so the convergence times would probably be a bit different. Also, depending on how you sample the bootstrap, you might have more or less bias. If you sample only 5 points, for example, I would assume that it's reasonably similar. Convergence, and there's all these numerical things that can go wrong, but it feels like it should be similar.
But this approach is more performant, would you say?
Hard to say. The thing is this approach is made, so my argument for this is this is very flexible. I can parallelize this, right? Well, bootstrapping can do that too, but I can do whatever mathematical system I want. Whereas for the bootstrapping system, you still need to be able to do, okay, data, model, do a gradient search, 1 point, and different data, model, 1 point. Whereas here I just say, okay, system, sample. It's again, I believe the results ought to be somewhat similar because you're doing a similar thing. You're trying to do some form of inference. So it'd be very surprising if the bootstrapping approach leads to a completely different conclusion than this. So yeah, I'm assuming that converges to the same spot. It's just that I'm not the most formal guy when it comes to maths.
Thanks very much.
If there are no more questions, then I think it might be nice to do some Bayesians versus frequentist jokes. Y'all ready? What's the downside of being a Bayesian? What is the downside of being a Bayesian? You have to explain your priors very frequently. Another question. What's the downside of being a frequentist? Why does a frequentist always make mistakes? It's because a frequentist has no prior knowledge. Thanks, guys.